Okay, is this about where we left off yesterday on polar, nonpolar? Yeah, pass the sentences into port if you would. You can watch them during beat time, Graham. Oh.
No, I guess it's right there.
Anybody have no idea what videos I'm talking about?
I watched 1.5. The third one felt super long. It was like the same thing over and over.
Hopefully it drilled a hole in your brain and implanted itself forever.
And then he was like, oh yeah, but that's not...
That wasn't very good handoff, was it?
That's not a covalent bond. Second one? He said one sentence, not a paragraph.
You're doing great, Levi. Don't let him tear you down.
That is my bad.
That was impressive placement.
That's two sentences. I only have one period.
There you go.
That's a lot of scribbles.
All right, we ready? Today we're going to cover, I don't know, not super hard stuff. Nothing way different. The goal at the end of the day is to make sure we understand polar and nonpolar, then that we're able to draw Lewis structures. Lewis dot symbols are easy. Now we're going to put structures together and throw molecules together. We'll see how it goes. All right, so turn to your lab partner real quick and tell them why or what it means to have a bond that is polar.
One of non-polar, is that what you said? Oh my god. Polar?
Polar.
Okay. One more or less going to get negative video.
What do you think, Donaldson? What makes it a nonpolar bond?
Nonpolar?
Sorry, polar.
The electrons aren't shared.
What?
The electrons aren't shared.
Okay, the electrons aren't shared equally. Good answer. All right, so here we go. Odds I pull that off, drop it on the ground. 80%. Okay, a polar bond. A polar bond is a bond between two atoms that shares electrons but does not share them equally. We know that they share because polar also has a word that comes right after it, which is covalent. Now, I didn't say this yesterday, but covalent, just the word is implying that you are sharing valence electrons. Co together, valent, valence. Okay? Your valence are literally together. You okay with that? No? June? Okay, thank you. If you do this, it might make sense. This takes a little time, but we'll do it. So 1s, 2s, 2p. And if I'm doing it for fluorine, which is a covalent molecule, if I put it with another fluorine, right? I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. You with me? All right. What we do now, give me just a second here. Now what we do, we have another fluorine that has the same exact problem. What is its problem? It has one box that's not all the way filled. All right? So all we do, all it does, and I know the letters are backwards now, but it just takes and it overlaps that P, and now both of them have a full P cloud. You with me? So covalent electrons, or molecules, they share their valence electrons. Easy enough? All right. Now, a polar like HF is one that does not share equally because F is super more attracted to the electrons than H. And understanding polar and nonpolar and ionic is really important. So here we go. Polar, that is terrible looking, but whatever. They have unequal sharing. Nonpolar has equal sharing, and ionic has no sharing. And we're talking about sharing of the what? The electrons, right? All right. The reason why polar shares unequally, nonpolar shares equally, and ionic doesn't share at all is all governed by this concept that we call electronegativity. It's the worst word to write in chemistry. So if I write E neg, I'm also referring to electronegativity. Okay? Because it's super long. It takes a lot of letters to type, and it's always spelled incorrectly in word processing things. I don't know like what chemist didn't consult them, but whatever. It's a word, I promise you. Electronegativity. All right, so let's just jump into electronegativity because it really is super important. It's very similar to electron affinity. So the ability of an atom and a molecule to attract electrons to itself is the definition of electronegativity. Now, if you don't have the notes in front of you, I would write these down. Everything on here is pretty important. Okay, so once again, electronegativity is the ability of an atom and a molecule to attract electrons to itself. All right, so once again, write the trends that on the periodic chart, it will increase as you go from left to right and from bottom to top. Or you can more simply just write that trend as an arrow that points from the bottom left to the top right. We okay with that? Now, every trend is a general trend. We're not going to worry about the exceptions here because it just doesn't matter to us. Just know that a certain type of element has a very high electronegativity and a certain type of other element has a very low electronegativities. So what ones have high electronegativities? Thank you. No. Non-metals. Riley, you still are getting referred to nowhere land. What are you even doing?
I don't know.
You just go to B time?
Yeah, I just want to.
Okay. And Bryce and Caden, same thing.
I don't want to go to this thing. Why aren't they yellow?
I don't know. To cheer up our day. Friday Yellow Day. What? Well, his official name is Caden. It's not my fault that his parents screwed up. All right. So here we go. Was that offensive? Okay, didn't think so. All right. So if you look on this next slide, I blew this up. Over here, we'll cut this off. This is the cutoff between what's and what's. Metals and non-metals. Whoops, that's an S. If you look, you will notice that family 8 is not included in this picture. Can you see that? Okay. They have essentially zero electronegativity. It's not really true, but essentially it's pretty much zero. All right, you will notice that metals, they have a very small. Blue is probably a terrible choice right there. They have very small electronegativities, and metals have very big electronegativities. Okay, not not the hardest thing to think about, because we know from our last chapter what about F? What is unique about it? It's really small and has the highest what? Okay, that too, but it also has the highest Zeph, right? Which means it's pulling its electrons the hardest of any atom on the periodic table. Well, what is electronegativity? It's the ability to attract an electron to it. So it should make sense that electronegativity and Zeph would be related to each other. Where were the things with the least or lowest Zeph? Where did they live? Right down here, right? Cesium has hardly any ability to hold on to its electrons. So that would make sense that in electronegativity it has a small value. It is not attractive to an electron at all. Yeah, it's super ugly. Windsor, did you figure out what your question was? They just cut out the ones that are radioactive on the bottom. Because really, francium is not really involved in chemical reactions like that we would ever do in class or in a lab. It's radioactive. All right, so here we go. To know whether it shares, we'll say share equally. Whether it shares unequally, that's a G, or whether it doesn't share at all, has everything to do with what we call the E-neg difference. So things that share equally have a small difference in electronegativity. So like if I ended up with nitrogen dioxide, or NO2, I would just simply look at the difference. N is 3, O is 3.5, so the difference between those two values is 0.5. You with me on that? That is a small value of difference in electronegativity, which means neither one of them is pulling on the electron significantly harder than the other. So where would the electron go? It'd just kind of hang out in the middle. You with me? All right, now, sharing unequally, like H2O, is going to have a medium difference in electronegativity. You can't see the H, it's right there, H2O. H is 2.1, O is 3.5. The difference between those is 1.4. Now, you would think it's a negative, but we're just finding the difference. There's never a negative value for a difference. All right? So 1.4 is considered a medium difference. So if there's this medium difference, then the one that's pulling harder is going to have the electrons more than the one that's pulling less hard, which means we make a polar covalent molecule. We have a positive side and a negative side. Now, no sharing is when we have a big difference. So if I had like cesium fluoride, I'd have 0.7 minus 4, and that's equal to 3.3. That is a very large difference. In fact, that difference is large enough that fluorine can completely remove the electron from cesium. And if it's removing it, is it sharing it? No, it's solid. But it's fine. Cesium didn't want it anyway. All right, now, I'm going to put this little slide up, but you don't have to have this memorized, but just feel it. To be nonpolar, you should have a difference between 0 and 0.6. To be polar, you should have a difference between 0.7 to 1.5. That's not right. Oh, poop. It's 1.7 here. Well, HF has a value that would be considered ionic, but it's a bond between two metals, which is always covalent. Non-metals, yeah, sorry. Yep. So here's an ionic bond. It's a difference that's greater than 1.7. Okay? Now, you don't have to have this memorized. What I would have you know is this. Just feel it, right? If it's a metal and a non-metal, it's ionic. Okay? And then this is a very generalized statement coming up. My thing's frozen. Let's see here. Come on, work, please. Okay, this, like I said, this is a generalized statement, but it'll get you through a lot. What the heck is happening here? The closer the non-metals to each other on the periodic table, the more likely they are nonpolar. So like their literal position on the periodic table in relationship to each other. What's that? Okay, Murray, you got to get out of here right now. Did you get hurt yesterday? Oh.
I've got to get doctor's notes.
Okay. Luckily that landed on my foot, so your iPad should be fine. Okay. He wrestles for a week and he's turned into that. Happens to the best of them, huh? Really? That's funny. All right. Anyway, the closer the things are on the periodic table, the more likely they are nonpolar. Then, I'll put a little asterisk here. If F or Cl is in it, it's most likely a polar substance. That sure looks like an IDS, but it's a T. Oh, I hate this erase function. I got this. Yeah, I don't even understand it. Whatever. That's a T. All right, it's most likely polar if it has F or Cl. Why would it make sense if it has F or Cl that it would be probably a polar substance? Okay, they are really big electronegativity values. So no matter what they hang out with, especially F, no matter what it hangs out with, it's going to make it polar. All right, now we're going to go over this for 2 chapters. So if you're not 100% with me right now, that's 100% fine. If you're like between 25 and 50% with me, then you're golden. If you're 100% with me, then take that chemistry drug every morning. All right. Now, just a little bit of notation here. When 2 atoms share electrons unequally, a bond dipole, that's the actual word, it means 2 poles. Okay, so that's not too hard. A dipole results. The dipole moment, or mu, and you don't have to do this math ever, so don't worry about it. The dipole moment produced by 2 equal but oppositely charged separated by a distance r is calculated as this, and it's measured in dBytes. Okay, what I would like to introduce to you is this thing that I just erased on purpose. But what you would do is you would draw an arrow indicating the direction the electron would go. And it always goes towards the more electronegative thing. Then the end of the arrow you would put a plus or a little line through to indicate that the electron moved this way, leaving this side positive. Okay? So dipole moments, math-wise, you don't have to do them. They're generally just an indication of what direction it goes, and then you put a plus just to indicate that that left that side positive. The greater the difference in electronegativity, the more polar it is. Like, you okay with that? We said that and drew it. All right. Here we go. The rest of the hour will be on this, and you should take notes. All right. Lewis structures aren't very complicated, but if you go home and try and do some and you forget the steps, then you're going to be completely lost. So, Lewis structures are representation of molecules, showing all electrons, bonding and non-bonding. Okay, yesterday I drew some of these, but also yesterday we mostly just talked about the Lewis symbol, so it would be H with a dot. That's the Lewis symbol for hydrogen. The Lewis structure for the diatomic molecule of hydrogen, you'd put the other H and then a second dot. Okay? Now, when you share electrons, you don't really even draw it as two dots. You put H, a line, and H. And you must, from now on and forever, realize that a line between two things represents a shared pair of electrons. So one line really means how many electrons? 2 electrons. You okay with that? Okay, so we connect things with lines to indicate the formation of a bond. Well, guess what? Lewis structures, they're amazing, and we normally only do them with covalent bonds. You can draw them for ionic bonds, but generally speaking, you would put it this way. Anybody know why? I told Windsor this yesterday.
Because the ionic one still the electrons, so
Okay.
it's not a shared.
Good. Because this line represents a shared pair, but in ionic, they're not sharing, they're taking. So you would have NaCl, and there'd just be 7 dots. Sorry, 8 dots now. You wouldn't put a line. You okay with that? Subtle difference, but important. All right, so here we go. This won't go away. I have no idea what it is. What if I can drag it? What the? I can't do anything to it, but whatever. Here we go. So these are the steps that, if I were you, I would write down. So when you're asked to draw a Lewis structure, the first thing that you need to do is determine the total number of valence electrons in your molecule. Now, this is a lot easier, the first part, than you think. All you need to know is the family that the thing is in, because family equals valence electrons. So phosphorus is in family 5. So that's where this 5 comes from. Chlorine is in family what? 8. audio. All right, sorry about that. Okay. So once again, if we complete it this way with those steps and everything works out, it's great. Let's do another easy one, which is CH4. I just barely had it, but follow the steps. Find the total number of valence electrons, put the one in the middle, connect them, octet, outside octet, inside, and see how it goes. All right, who's done with CH4? All right, it looks like most of you. Okay, it was simple, but following the steps, we'd have 4 valence electrons. Hydrogen would have 1 valence electron, but there's 4 of them, so this adds to be 8 valence electrons. The central atom has to be who? Carbon, because hydrogen can't ever. So I put the 4 hydrogens around it, and I connect them with a line. By connecting each with a line, I just used up 8 valence electrons, right? So I have 0 left, which might be a problem. I did not octet the hydrogens. Okay, they don't get octeted, which is probably not a word. They just get deuced. I don't know. They have 2. All right, so they're happy. Does the carbon have the 8 it wants? Yeah, sure does. So then this would be a complete octet on carbon, and hydrogen would have its S block filled. Life would be dandy. Easy enough? Okay, now, you got to make sure, like it says, to keep track of your electrons. If you don't, you'll get in a big amount of trouble in a hurry. Okay, now, there's what happens when you run out. If you run out of electrons before the central atom has an octet, you have to form multiple bonds until it does. So let's work through this together here in a second. But write this down, that's a rule. If you run out of electrons before the central atom has an octet, you have to start sharing more electrons. All right. So if you just follow the steps with me on the next slide, hopefully this will make sense. And it probably already does anyway. But we have H, C, N. The steps would be to count the valence electrons. 1 plus carbon has 4 plus nitrogen has how many? 5. So this equals 10, correct? All right. So now the central atom is the most electronegative that is not, least electronegative that is not hydrogen. So that ends up that it has to be the C, because if you look on the periodic table, it's more to the left. So I just have my H, my C, and my N, and I connect them each with a line. All right. So I've already used up how many electrons then? 4. So I'm left with 6. All right, the next step would be to complete the octet on the outer atoms. Hydrogen's fine. I complete the octet on nitrogen. How many did I just use to do that? 6. So I subtract and I get 0. Now, that would be dandy, except for what's the problem? All right, I don't have my central atom octetted. So if I run out before I can put an octet there, then I have to start making multiple bonds. So let me get my handy eraser out, and I'm going to erase 2 pairs. And I'm going to put 2 lines right here. That gives nitrogen 8. That gives carbon 8. And it gives hydrogen the 2 that it wants. We all right with that? Okay. This dumb thing. Whatever. All right. So it's not the hardest thing, hopefully, we've ever done. Let's see if you can draw carbon dioxide. So come up with the Lewis structure for carbon dioxide for me. This is very pretty.
Thank you.
Mm-hmm. You got this? Okay. Looks like pretty much everyone I looked at has it just fine. All right. There's actually 2 options for this. Did anyone do it one way and their partner did it the other way? All right. So let's follow the steps, because if we follow the steps, we're less likely to screw up. How many valence electrons in carbon? 4. How many in oxygen? 6 times 2, because there's 2 of them. That's 12 plus 4. That is 16. Correct? All right. So now, carbon has to be the central atom, because there's 2 O's and only 1 C. So I have an O, a C, and an O. And I connect them with a line or a shared pair. So now I have to subtract 4 right off the bat. And that is 12. Then I need to complete the octet on each outer atom. All right, that would be 12, and I'd get to 0. And then we have the exact same problem we had with our last one, correct? We cannot octet carbon. So what we will do is we will then actually have to erase a pair, and we're going to erase a pair on both sides and share a pair on both sides. Now carbon has 8, oxygen has 8, oxygen has 8, and life is great. Now, there is a thing here I did at the end of the hour yesterday. I have 16 total electrons, right? To octet 3 things would require how many, though? 24. What's the difference between these 2 numbers? 8. That means I need 8 shared electrons. How many did I share? 8. Okay. Now, did anyone do this? Did anyone do that one? This one is sort of okay. This one works, but this one's right. Okay? So how would we know which one was more right than the other? All right. You would think. But we're going to talk now about formal charge. You only have to check formal charge if you had to make a double bond or triple or whatever, but a lot of times you do not have to worry about formal charge. Sorry, boys typing. There is a whole slide for it. It's the next one. Okay, so formal charge will help us decide between two of them that work to know which one is right. And it's this concept right here. All right, and it's really the next step. Is we did our bonds, then we need to assign formal charges. And this is saying the formal charges you only have to do when there's two or more possible correct Lewis structures. And hopefully this makes sense. Now, it's a sub-process in a lot of processes. I know that I'm overwhelming you a little bit with things, but if you write them down, it's not hard. So like this would be a more indented bullet on your list of bullets. That make sense? All right, so for formal charge, you need to do the following. For each atom in the molecule, count the electrons in lone pairs and half the electron it shares with other atoms. So what it's saying is for oxygen right here, it has 1, 2, 3, 4 that are alone, and then 8 that are shared, right? Or sorry, 4 that are shared. You with me? 1, 2, 3, 4, and then 4 that are shared. So I take the 4, and then I add half of the shared, which is 2, and that equals 6. So in this version of CO2, both these oxygen have 6 assigned electrons. How many assigned electrons in carbon then? There's 8 shared electrons, so it's half of that, so it's 4. You okay with that? Now, in this version of oxygen, you have 1, 2, 3, 4, 5, 6, and then half of 2. So here you have 7 that are assigned. And the carbon still has 4. But this oxygen, you have 1, 2, plus half of 6, so you get 5. Okay, that's how we calculate assigned. All right, so the first thing you need to do is find out the numbers that are assigned, and then you subtract them from the number of valence electrons for that atom. So the valence electrons for oxygen was 6. In this model, the assigned were 6, so you subtract and you get a formal charge of 0. Carbon, 4, 4, and 0. Oxygen, 6, 6, and 0. Over here, though, you had 6 and 7, and you end up with a -1 formal charge on this oxygen. And over here, you end up with a +1 formal charge on oxygen. Now, oxygen could not care less if it has a negative charge. It's actually pretty happy about that. But does this oxygen, is it happy about having a positive charge? No. Oxygen is the third most electronegative atom on the periodic table. Is it going to be made to be positive? No, you can't remove an electron from oxygen if you're carbon. Oxygen can remove it from you if it wants to, but this doesn't work. So when we have two Lewis structures that will work, we select the correct one to be the one that has the fewest numbers of formal charges. So this has 0. Or we choose the one that puts the negative on the most electronegative atom. And that's on the next slide, so don't worry about it. All right? So it's the one with the fewest charges or the one that puts a negative charge in the most electronegative atom.